In this lesson, we're going to look at alkene reactions that result in Markovnikov addition. Let's look at the reaction called hydrohalogenation to see what this even means. We'll start with this alkene. It's unsymmetrical. We have two methyls on this side and just one on this side. If we look at the carbons of the alkene, we can see 1, 2, 3, 4 bonds drawn out here. And for this one, we only have 3. 1, 2, 3, 2 from the double bond. So here we have an implied hydrogen. And when you're starting out with these reactions, I want to encourage you to always draw in your hydrogen atoms. It may seem cumbersome and take a little time, but is going to prevent you from making a mistake. So let's add in our hydrogen atom. Now we're going to react this with hydrochloric acid. And the ultimate result is that HCl is going to add across this bond, giving this product. Now I want you to notice where these groups added. So the chlorine added to the more substituted side of the bond where we already had 2 methyls. And the hydrogen from the HCl added to the side where we already had a hydrogen atom. And this is the definition of Markovnikov addition. We get addition of the hydrogen to the side that has more hydrogens to begin with, the less substituted side of the alkene, and the chlorine adds on the more substituted side. We need to look at a mechanism to see why this occurs. Alkenes are nucleophiles. They have electrons in this bond that they can donate. So in the first step, what's going to happen is this double bond is going to attack the proton of HCl. And our arrow pushing is going to look like this. The alkene opens up, attacking that hydrogen atom. Now these electrons will be left behind and we'll show them becoming a lone pair on Cl-. Now when these electrons come and attack this hydrogen atom, they pull away from this carbon. We're making the new bond on this side, so the electrons are coming away from here. Notice we have this carbon now that only has 3 bonds, and we're sure of this because we drew out all our hydrogen atoms through the process. Well, carbon is neutral when it has 4 bonds, and this only has 3. The electrons shifted in this direction to make the new bond, leaving this carbon deficient of electrons. So this structure has a carbocation right here. This carbocation is what we call tertiary. It's bonded to 3 carbon atoms. That's really good for a carbocation. There's a process, an effect called hyperconjugation that allows the CH bonds to stabilize. So these CH bonds here to stabilize this carbocation. We're not going to go into that in too much detail, but you can Google it if you want to know more. And so a tertiary carbocation is really stable, very good. More substitution allows for more stabilization of a carbocation. Now the chlorine can come back in and an electrostatic attraction bonds to this carbon atom here. Markovnikov addition is a specific regiochemical outcome. The chlorine adds to the side that's more substituted and the hydrogen to the side that's less substituted. But why doesn't it ever flip? Why don't we get the hydrogen adding to the other side? Well, we'd have to imagine the alkene attacking in this direction, opening up in this way. And let's just draw what we would get over here. So here, we're envisioning if this double bond opened in the opposite direction, putting a hydrogen on this carbon atom here, we would get this intermediate. Notice this carbon containing the carbocation. It's bonded to a hydrogen. And then it's bonded to 2 other carbons. This is what we call a secondary carbocation. And we said over here that these CH bonds are particularly stabilizing to this carbocation. And here we have 1, 2, 3 carbons bonded to the carbocation. This so-called tertiary carbocation is much more stable, and that's why the bond will actually open in this direction to produce this more stable carbocation. So you can think about this in a couple ways. There's a trick to thinking about Markovnikov addition, and that's the rich get richer. And so the carbon that had more hydrogen atoms gets the hydrogen atoms. So always attach to the side that already had hydrogen atoms, and that'll give you your correct regiochemistry in your product. But this really has to do with carbocation stability. So if you want to understand it, always make your more stable carbocation when you do your alkene attack. Okay, let's get into our second reaction for today, hydration. We're starting with the same substrate that we had here. However, I've left off all of the implied hydrogen atoms and I've abbreviated the carbon as sticks. This is a notation that you're going to have to get used to, these abbreviated structures. And so let's try to look at this mechanism just using the structure like this, but keeping in mind it's the same structure as here. We're going to treat this with sulfuric acid in water. And the ultimate result of this reaction is Markovnikov addition of water across this double bond. So we can see that our OH is on the same side as our chlorine, so this is going to tie right into the mechanism again. And this side now has two hydrogen atoms. Notice it's kind of hard to see this, so when you're starting out, do yourself a favor, draw out all your hydrogen atoms. It may seem cumbersome, but if it prevents you making a mistake on an exam, it is so worth it. Okay, let's see why this reaction goes the way it does, looking at the mechanism. I'm just going to show a proton to represent the proton that comes off of sulfuric acid, and our alkene is going to open up to form the more stable carbocation and attack that proton. So here's our tertiary carbocation, here's the new proton. Notice there's only 1, 2, 3 bonds to this carbon, so I've left off the other proton. For clarity, let's just add that in right now. And now something different is going to happen here. We attacked an acid that has a nucleophilic conjugate base. Chlorine is a nucleophilic atom, and so it adds to the carbocation. But once we take the proton off H2SO4 and we get HSO4-, that is really resonance stabilized. It is not a nucleophilic acid. So sulfuric acid, the conjugate base of sulfuric acid, doesn't add back in. Instead, we have water in here. That's our good nucleophile. And this reaction will be run in water, so there's lots of water around to now attack this carbocation. Water is going to use one of its two lone pairs to attack the carbocation. So we're going to connect this oxygen atom over on this side. Now, there's something really important about mechanisms, and this is always going to hold true, so I want to tell you about it right now. Here we have something positive, a carbocation. It's interacting with something neutral, this molecule of water. Whatever comes out of this reaction has to have an overall +1 formal charge somewhere. So if you've drawn this without a +1 charge, you have a +1 reacting with a neutral, this has to be positive. If the thing you've drawn is not positive, you've either drawn it wrong or you've forgotten to write a second product of that step. And in this case, I had left off the positive charge on oxygen to make this point to you. Now, oxygen is neutral when it has its two lone pairs and then these two bonds. So if we're counting valence electrons, that's 2, 4, and half of these bonds make 6. Well, when it shares a lone pair, it only has 5 electrons that it owns around it, the lone pair and half of each of these 3 bonds. So this is positive. And this truly holds in every mechanism you'll ever write, that if you have a positive reacting with a neutral, you get a positive negative with a neutral gives you a negative. So make sure you're checking every step for your charge balance. Now, we haven't quite gotten to the product here because it's charged, and the ultimate product is an alcohol. So our best nucleophile, which is still water, the thing that attacked with its electrons, is going to come in and deprotonate this. It's a nucleophile. Anything that ever attacks has to have extra electrons to attack with. And so these electrons will grab this proton, deprotonating it, And in every mechanism where we have electrons left behind, we show them becoming a lone pair on the atom that they're left on. And in this case, we can see how it neutralizes the positive charge on oxygen. And then we get a neutral molecule out. Wait a second, I just spent all this time telling you a positive reacts with a neutral to give a positive overall. Well, in this case, we've drawn this correctly, but there are two products. The hydronium ion is the second product produced in this reaction. And so we are actually getting two products from the reaction of a positive with a neutral, and we got a neutral and a positive out. So overall, this was +1, the products are +1, and everything is right with our mechanism. Okay, we're going to look at one final reaction in this lesson. This is oxymercuration, and this is going to do Markovnikov addition as well. Let's start with our same substrate. The ultimate result is going to be the same alcohol as we produced up here from the hydration of this alkene. But this is a really different reaction with a distinct mechanism. Let's look at how it works. We first treat this alkene with mercury acetate in water. Now the alkene is going to attack the mercury and kick off one of the acetate groups. Can you guess which direction it opens up in? The rules from here still apply. We're going to attack to form the more stable carbocation. So the mercury has added over here. We have this carbocation. For clarity, let's add in the proton here so we don't lose track of our bond. Now, this intermediate is special. This isn't the whole story with its structure. Mercury can actually donate electrons in, stabilizing this carbocation. This gives another resonance form for this compound. So imagine mercury shares some electrons over here. We'll get a resonance form with a mercury bridge. Now we're just moving around electrons, so since this was positive, the same story with the steps of a mechanism for resonance structures applies here, and we need a positive charge in this. Mercury shared the electrons, and the positive charge is now on mercury. This is called a mercurinium ion, and this contributes a lot to the overall structure. However, it's in resonance with this carbocation. We could actually draw a third resonance form that puts it in resonance with the secondary carbocation, but we know that these two are the main contributing forms because this one has the positive charge on mercury, and mercury is good at that. This is just a new thing that we'll have to learn here. But everything we learned before still holds, and this is our more stable carbocation. So although this structure contributes, when water attacks, it still wants to attack at the carbon with more positive character. So water attacks, opening up the mercurinium ion, and we actually get this protonated intermediate, but I'm going to cheat and below my arrow put a -H+. So we'll skip the deprotonation step here and go right to this alcohol. And now we still have mercury stuck on our molecule, but we're going to get a hydrogen atom here. This is a new reaction. We can treat this with sodium borohydride, NaBH4, in a second stage of our reaction, and the hydrogen on here is going to replace the mercury. And we get our alcohol resulting from Markovnikov addition overall. Okay, so why on earth would we ever want to do this reaction? This results in the same product as acid-catalyzed hydration here. And so why bring heavy metals into it? Why have to do a second step with sodium borohydride? Why would we do any of this? Okay, let's look at an example that shows us when oxymercuration will be useful. Imagine we have this substrate, and we want to add water in a Markovnikov fashion across this double bond. On the surface, this seems just fine for acid-catalyzed hydration. We get the hydrogen atom adding to the least substituted end of the double bond. The OH group goes on to the more substituted side. But as you can imagine, if I'm showing you this, there's more to the story than that. Let's look at the mechanism and see what actually happens if we try to do this under acid-catalyzed hydration conditions. The first step is the same. Our alkene opens up as normal, attacking the proton. Now we get the secondary carbocation. Now this secondary carbocation is next to a branch. Now if this hydrogen atom were to move over with its electrons, we can actually make a tertiary carbocation here. And this is some of the toughest stuff that you'll first encounter with these reactions of alkenes, so don't be discouraged if this is a little bit new to you right now. But since we have the positive charge here, if this hydrogen moves with its electrons as a hydride, H-, we'll show this migration as these electrons coming right over here. And just for clarity, I want to add on the hydrogen right here on this carbon. And we'll add it here, so now we can see that this has 4 bonds. But since this moved away with its electrons, it's going to leave a carbocation here. This 1,2 hydride shift is common in chemistry and biochemistry, and the way we can spot this is, I said we made this secondary carbocation next to a branch, so we can actually get shift of a hydrogen or sometimes shift of a methyl group to give a more stable carbocation right next door. And so you have to watch out for any sort of branching next to a carbocation. And if movement of something can make a more stable carbocation at the adjacent position, that'll happen under acid-catalyzed conditions. So now water attacks here at the carbocation. We lose a proton, and the product that we get from this reaction is this. So we just wanted to add water across this double bond. It looks so simple, but we had this complicating rearrangement reaction. So getting back to this question, why oxymercuration? It'll actually make this reaction go with the regiochemistry that we wanted. The OH will just add here. Oxymercuration avoids rearrangements. The reason for this is in the mercurinium ion. Although we have contribution of this carbocation, this mercurinium ion contributes a lot as well. This stabilizes the carbocation, and when this is more stable, it won't want to rearrange. So if we take this alkene, treat it with mercury acetate in water, and then in a second step add sodium borohydride, we'll produce this alcohol not resulting from rearrangement. So in this lesson, we covered the reactions of alkenes that result in Markovnikov addition. The real reason for this is we're producing more stable carbocations from our initial attack. These all always open up in the same way when the alkene is attacking something. The addition puts the nucleophilic group at the more substituted carbon atom in each of these cases. But oxymercuration avoids carbocation rearrangements because this mercurinium ion can form and stabilize this carbocation so nothing can rearrange around it. This is kind of a weird intermediate, this 3-membered intermediate, but this is part 1 of a multi-part video series on alkenes, and we're going to see that these bridging cationic intermediates are very important in alkene additions. And I hope you'll join me for the next video.